What's up, dudes? I don't know. I'm like blending into the background right now. It's because I'm wearing this shirt and I don't have everything all tuned up right. And, it's fine. It's totally fine. We're going to be okay. You don't really care. I'll be a floating head. It'll be good. We're talking about, is that spe? I don't think that's how you spell special. Just maybe. Anyway, like I was saying, that's not how you spell special. Uh, but we're gonna roll with that too. I may fix it when I actually release the video. You notice that I now have headphones on. It's because while I was paused briefly, laughing about Speckale, a scammer called me named McDaniel. I've never heard of a person named McDaniel. That's what I told them. They hung up on me. It was very rude. Anyway, we're going to talk about special right triangles. Let's jump right in. This video is getting off to a great start. We're doing really well. It's Friday afternoon. I'm tired. My wife is out of town and busy and all the things, but we're going to get her done. So let's do it. So there are two special right triangles we're going to talk about. The first one is a 45, 45, 90 triangle. Where does it get its name, you might ask? Well, that's fairly obvious when you look at the example I have here. So a 45, 45, 90 triangle is also also could be called an isosceles right triangle because base angles equal, which means the sides are equal. So the whole point of this lesson, the whole point of special right triangles is they are two triangles that have angles that have set ratios that are exact. And this may be the first time you've learned about them. If it is, that's great. If not, that's also fine. If you've seen them before, that'd be even better. But excuse me. But at this point, special right triangles are some trig ratios that you need to memorize, and that's kind of one of the important bits. And so we're going to kind of build up what these ratios are. All 45, 45, 90 triangles are all similar, which means they all go down to this ratio. So this is an isosceles right triangle. It is a 45, 45, 90 triangle, right? And so we're going to kind of pick some numbers to get reduced here. So if we say this is 1, right, then this one would also be 1 because this is an isosceles triangle. So how would we find this third one? Well, we could use the Pythagorean theorem, right? So 1 squared plus 1 squared would equal c squared, right? 1 squared plus 1 squared is just 2 because 1 squared is 1 plus another 1 is 2 equals c squared. Now, if we were going to solve for c here, we would take the square root of both sides and end up with c equals the square root of 2. And this is how the ratio for a 45, 45, 90 triangle works. It is 1 and 1 for the legs, and then square root of 2 is the reduced ratio for the last side. I think we're heading to examples next. Let me see. I prepped this file a few days ago, and I'm just now getting around to making it. So, yep. So let's look at some examples of how you might use that. So we're supposed to find x, and you may or may not, whether it says this or not, we want to give your answer, not example, give your answer in exact terms. Struggling here. Answer in exact terms, right? So we don't want to like get the decimal equivalent, that square root. Exact terms. That's what that means. And always when we're doing problems with special right triangles, we want that. We don't want the decimal equivalent. Now, it's worth noting, for those of you who are in my class, there will be a section on this exam that is calculator free, where you don't get to use a calculator, and it'll be because of this right here. It'll be a little section of special right triangles. So anyway, so for this first example, this is a 45, 45, 90 triangle. We know that because this is 45 and this is 90. So 45 plus 45 is 90. So that's what the kind of triangle this is. Also the point of the lesson, right? So these two sides are the same. So this one is 6. It's not actually asking for that. But to find this last one, we multiply whatever this is times the square root of 2. So in this particular example, x equals 6 times the square root of 2. And that's all there is to that. 45, 45, 90 is 1 square root of 2. So if we're given the sort of x side, the 1 side, then to find the other one, we do 6 times, or we do that times the square root of 2. Easy peasy. So this one, this time we are given the legs. So we're given that 1 side. So, this one would be this times the square root of 2. So how would we do that? So just like this one, we would do this leg times the square root of 2. So x would equal 9 square root of 2 times the square root of 2. Now this one we can simplify, right? We're not as simple as we can get. In fact, it's going to simplify out really nicely. So we've got x equals 9 times the square root of 2 squared. Why is it the square root of 2 squared? Because the square root of 2 times the square root of 2 is the square root of 2 squared, right? That's how squareds work. Square and square root, what do? Well, they cancel, of course. So we end up with 9 times 2. So 9 times 2 is 18. So x in this problem is 18. That's easy peasy. Now, if we were given the hypotenuse and we were trying to go back to one of the legs, we would instead divide by the square root of 2, which would probably mean rationalizing the denominator, which we'll look at in a later example if I'm not greatly mistaken. Again, I prepped this file a few days ago, and here we are today. So the next example, oh, look at that. We're going to have another example that is basically exactly what I'm saying. I forgot that even existed. That's great. Let's do it. So this time we're given a 45, 45, 90 triangle. And you say, how do we know that? Well, it's isosceles, and it's a 90-degree triangle. So and we know it's isosceles because this one's x and that one's x, right? So it's also a 45, 45, 90 triangle. So this side is the square root of 2 side, and this side is the 1 side. So to get from this one to that one, instead of multiplying by the square root of 2, we are going to divide by the square root of 2. So it's going to be 12 divided by the square root of 2. Now, we don't like to leave square roots in the denominator, so we have to rationalize that denominator. So how do we do that? That's easy peasy. We just multiply the top and bottom times this square root. So we're going to multiply times the square root of 2 over the square root of 2. So in the denominator, we have the square root of 2 times the square root of 2, which is the square root of 2 squared. Square and square root cancel, leaving us with just 2. So we get rid of that radical in the denominator. And then in the numerator, we've got 12 times the square root of 2. And then we just said over 2. Can we reduce this any further? Yes, in fact, we can, because 12 divided by 2 is 6. So our final answer is x equals 6 times the square root of 2. Great. Easy peasy, lemon squeezy. We've got one more type of special right triangle. That is a 30, 60, 90 triangle. Now, we've got a couple of different things on this page. Right? Every time I look at myself on the screen, floating in the whatever. It's fine. It's fine. Hopefully it's not distracting to you. It's distracting to me every time I see it, but maybe you'll just get used to it and not worry about it. Anyway, what kind of triangle is this? This one right here. That is an equiangular, aka equilateral triangle, right? 60, 60, 60, right? Which means that this is congruent to that, is congruent to that, is congruent to that, right? So all the sides on this triangle are congruent to each other. Now, on this one, to kind of get a reduced ratio, what we're going to do is we're going to say that, okay, what if we said all the sides are equal to 2? Now, why are we saying that? Well, because when we cut this in half, making a 30, 60, 90 triangle, now we have a side that has a length of 2 and a length of 1, right? Because that 1 is half of that 2. So that's why we made these sides 2. right? Now, we need to know what this one is. I already know in my head, but let's work it out with the Pythagorean theorem. So working it out with the Pythagorean theorem, we've got 1 squared plus x squared, or let's call it b squared. That seems reasonable. Equals c squared, which is 2 squared. 1 squared is 1 plus b squared equals 4, because 2 squared is 4. If we subtract 1 from both sides, we end up with b squared equals 3, because 4 minus 1 is 3. Take the square root of both sides, and we end up with b equals the square root of 3. Now remember, as we're looking towards the future, when we take the square root of both sides, we actually get plus or minus, but we're going to throw out that minus because we're talking about distance, right? So the ratio, the reduced ratio for a 30, 60, 90 triangle is 1 for the short leg, and I'm going to kind of label that on these ones because we've got kind of more things going on, right? We don't have just 2 things. We've got 3 things. So the short leg is the 1 leg. You might could call it 1x, if you will, right? Or just x even, right? The short leg. The long leg is square root of 3x, right? So if we're given this, to get this one, we just multiply it times the square root of 3. And this is, of course, the hypotenuse. Hypotenuse, which I'm going to abbreviate. We're going to get used to that abbreviation for hypotenuse a lot. Okay, so that's how the ratio works for a 30, 60, 90 triangle. Let's look at an example using one of these. Okay, so this time we want to find x and y, and this is the triangle. This is a 30, 60, 90 triangle. We know that because this one's labeled 90, this one's labeled 60, and 90 plus 60 subtracted from 180 is 30, right? So this is a 30, 60, 90 triangle. So let's identify our legs and our hypotenuse, right? This is the hypotenuse. So if we're writing our ratio, this would be the 2 side. The short leg is right here. So this is the 1 side. And this one right here is the square root of 3, the long leg side, right? So that's our ratio that we're basing this on to get what we're doing. So we're given the square root of 3 sides. So to get back to the 1 side, the x side, and that's often what we're wanting to do. If we don't have that sort of x side, because both of the 40, 45, 45, 90 and the 30, 60, 90 both have 1 or 2 sides where the ratio goes down to 1. If we're not given that, usually trying to get to that one first is a good idea, because that's going to be kind of our unit rate, if you will, kind of, to use that kind of an analogy. So to get from here to there, we're going to divide this by the square root of 3, right? So to get to x, we're going to divide 15 by the square root of 3. So x equals 15 divided by the square root of 3, right? So we got to rationalize that denominator, multiply top and bottom times the square root of 3. Which on the denominator, we already saw how that works. Square root of 3 squared, square and square root cancel, leaving us with just a 3 in the denominator. So that equals just a 3 down there. So 15 times the square root of 3 is 15 times the square root of 3, right? Not rocket science. It is math, though. All over 3, right? Square root of 3 squared is just 3. Now, can we reduce this? Yes, in fact, we can, because 15 and 3 reduce to 5. So x in reduced form equals 5 times the square root of 3. Great. Let's look at x. So now that we have the 1 side, the x side, it is the x variable in this problem, but just that 1 side, to get from to other ones, we just take and multiply times this one times whatever it is. So if we didn't know this one, we would multiply times the square root of 3. And if we didn't know this one, which is true here, we'd multiply by 2. So y equals 2 times that one. So 5 times the square root of 3. And that's easy peasy, right? We just do 2 times 5. So it equals 10 times the square root of 3. Great. And that's really all there is to special right triangles. That's a pretty straightforward one. In the next one, in our next lesson, we're going to learn actual trigonometry, learn trig ratios, SOHCAHTOA, sine, cosine, tangent, all that fun stuff. It's going to be great. We'll see you there. Have a great, grand, and glorious day.